Hello and welcome to the lecture series on applied thermodynamics. In today's lecture we are going to begin with a new module and new chapter. This chapter is about psychometry and air conditioning. Before we proceed further, let us look at the objective of today's lecture. In today's lecture we are going to look at an introduction to psychometry, followed by properties of moist air. So now let us look at what exactly is psychrometry and what is its relevance. We know that in the atmosphere we have atmospheric air, and this atmospheric air has two parts. One is the dry air, and in the dry air we have some presence of moisture which is called as vapor. So we have here an illustration that in the atmosphere we have atmospheric air. If it is not having any moisture, then we call it as a dry air, and on the other end we have some presence of moisture or vapor, and the contribution of vapor into the dry air depends on the climatical conditions. Therefore, when we consider dry air and when it is combined with a vapor, then we get sum of dry air and water vapor. So this is called a mixture, air plus vapor mixture, or in other words it is called as moist air. Please remember that moist air is a sum of dry air and water vapor, and psychometry is a study of moist air and the properties of the moist air. So now one can express the state of the dry air as the pressure of the air as a lowercase pressure. It is having some partial pressure, and we know that dry air is composed of different type of gases, atmospheric air, and it is, if it is considered some volume, then we can say volume of dry air. Similarly, the mass of that air we can call it as small m to the suffix air. So we have P of air and V of air and mass of air. So all these air are representing dry air in the atmosphere. So partial pressure of air, the volume of dry air, and the mass of dry air. Likewise, when you consider vapor, there also we have partial pressure of vapor, and we have the volume of that vapor, V to the suffix vapor, and then the mass of that vapor as mass to the suffix V, mass of vapor. Likewise, when we combine dry air and the vapor, likewise for pressure, we can write as a mixture pressure. Mixture pressure, or the total pressure, is equal to the sum of dry air plus the partial pressure of the vapor. So we have pressure of dry air plus pressure of vapor. Likewise for the volume also, when we add these two, then we get volume of the mixture, which is a sum of volume of dry air plus this vapor volume. Likewise, the mixture of the mass, total mass, in other words, is equal to sum of mass of dry air plus mass of vapor. So we can, and we also understand that for air conditioning application, generally the temperatures that we encounter are usually less than 40 degrees Celsius, and also the vapor which is present in the atmosphere is at a very low pressure. So looking into these two aspects, one can model the air or the moist air as an ideal gas. So now let's move further and look at the psychometry definition. So we have a psychometry is a study of moist air, the properties of moist air. It is useful to engineers, especially those who are concerned with heating applications, cooling application, and ventilation of building shapes, and aircrafts, etc. And since we see that moist air is usually at a lower pressure, we can model it as ideal gas, and we can apply ideal gas concept to it and derive some important relations. Now let's move further and look at some of the basic definitions related to psychometry. So let's first look at what is a dry air, followed by moist air, and then the saturated air. So let's see what is dry air. And we know that atmospheric air is composed of mixture of many gases, like we have a nitrogen, a huge part of it, and then we have oxygen, followed by argon, carbon dioxide, and so on. And at low temperatures, usually for this air, we consider a constant specific heat of 1.005 kilojoule per kg Kelvin, and in the dry air we have no presence of water vapor, so there is no presence of water vapor. So that is important when we are considering dry air. And since there are many gases, so therefore we have a partial pressure existing in the dry air. Now moving further, what is a moist air? So moist air is basically it's a mixture of dry air and the water vapor, and it is assumed to be behaved as an ideal gas at states under concentration. So this is about the moist air. So now we understand what is a dry air and what is a moist air. So for our study we are concerned with the moist air, and we'll see how exactly the vapor content or water content in the moist air is going to vary, and its effect on the heating or cooling or the required situation. Let's now move ahead with what is an unsaturated air mixture. We know that air is now having some amount of moisture, therefore we are calling this as a moist air, and that will be our sample. And unsaturated air mixture, it means that we have a moist air sample, but the amount of vapor inside this sample of air is not sufficient enough for it to become saturated. So such a state we call it as unsaturated air mixture. Usually this is on the superheated zone. On a TS plot, when we have a saturation dome, we know that if the system is existing on outside the saturation dome on the right side, then we call this as a superheated zone. Usually this unsaturated air mixture is on the superheated region. So it is a mixture of dry air and superheated vapor, in which the partial pressure of vapor is being less than the saturation pressure of water at the temperature of the mixture. Now let us look at what is saturated air mixture or saturated moist air. In other words, air mixture here represents moist air. Similarly, likewise here, unsaturated air mixture represents unsaturated moist air. So it is a mixture of dry air and water vapor, but in this case the partial pressure of vapor is equal to the saturation pressure of water at a temperature of the mixture. Now the concept of these saturated air mixture and unsaturated moisture becomes equal if we becomes clear to us if we look at it on the TS plot. So let us now look at a TS plot. So here we have a TS plot, temperature versus entropy, and we have a saturation dome, and we know that the right side curve, what is being shown on the saturation dome, this is a saturated vapor curve, and we know that on the left side we have a saturated liquid curve. So at this point we have the saturated liquid point, and as we go on adding heat to the system, though there is a vapor formation, and then we see that all the liquid gets converted into vapor at state point 2. So this is a dry saturated curve. So this is the point of interest here, where we know that condensation begins at point 2 if there is any further cooling from this. Now so here we have a moisture sample, state point 1 representing a sample of moisture, and we know that moisture is a combination of dry air and the water vapor, and the vapor which is there at state point 1 is in superheated level. That means it is invisible to us, and we know that this water is at a pressure, and this is called as a vapor pressure, partial pressure of vapor. It's a lowercase p, partial pressure of vapor in the sample of moisture. And when we look into the pressure curves, it becomes very clear to us that the partial pressure of vapor is lesser compared to its saturation pressure. So this vapor which is in the state point 1 gets saturated when it approaches to the saturated liquid core at state point 2. So this is the point where the pressure is the saturation pressure of the water. So the vapor is going to get saturated completely at state point 2. So that means the partial pressure of vapor is lesser compared to the saturation pressure of the mixture. So that is the meaning of. So and this becomes very clear to us, like we have a pressure curve here, and as we approach from state point 1 to the dry saturated curve, it has to pass through many pressures, or in other words, moisture has to keep on adding to the sample so that at point 2 it becomes completely saturated. Therefore we can write it as saturation, the partial pressure of vapor in the moisture at state point 1 is lesser than to its saturation pressure of the mixture, which is at this point. Likewise, we know that the total pressure or a mixture pressure is represented as a sum of the partial pressure of the dry air plus the partial pressure of the vapor. So this is a general equation which we have seen earlier. Now for a state point 1, we can write from this equation, we can rearrange this equation, and we can write it as the partial pressure of dry air is equal to the pressure of the water minus partial pressure of the vapor. So this represents the state point 1 at state point 1. So now at a state point 2, suppose if the water, if the moist air sample is existing at state point 2, for example, then we know that at state point 2, since it is on the dry saturated curve, the partial pressure of vapor is equal to the saturation pressure of the sample. So therefore both are equal. So partial pressure of vapor becomes equal to the saturation pressure of the sample at state point. Therefore for state 2 we can write it as the same equation what we have here, total pressure. We can rearrange this. The only difference is we are going to now equate the partial pressure of vapor to get equal to partial pressure at saturated condition for the sample. So then we have the partial pressure of dry air will be equal to the total pressure minus the saturated pressure of the sample. So that likewise we can express at state point 1 what is the condition of pressures, partial pressures. So this is about the saturated and unsaturated air. So we recall that at state point 1 the sample of moisture is unsaturated. That means more amount of moisture can be added to bring it to saturation condition. In other words, the sample becomes completely saturated when it approaches the saturated liquid curve at state point 2, where the partial pressure of vapor becomes equal to the saturation pressure. So with this, friends, we'll proceed further, and along with this, to study the psychrometry, it is useful to consider two temperatures, and we have one setup here, and this setup is called as a sling psychrometry, psychrometer, in other words, sling psychrometer. So we have two thermometers here which are set side by side. One thermometer is called as regular conventional thermometer, and the bulb of the thermometer is just open to the ambient, and therefore the temperature that is indicated by this conventional thermometer is going to be called as a dry bulb temperature and the dry bulb thermometer. On the left side we have another thermometer here, and this thermometer has a wetted cotton wick which is fully saturated, and this is wrapped around the bulb of this thermometer, and whatever the temperature that this thermometer indicates is called as wet bulb temperature, and therefore this is a wet bulb thermometer. So we see a basic difference here between the dry bulb temperature and wet bulb temperature. In case of dry bulb temperature, the thermometer is simply exposed to the ambient condition and the dry condition completely, and in case of wet bulb thermometer, the bulb is wrapped with a cotton wick which is completely saturated in water, and therefore the temperature that is indicated by this thermometer is called as a wet bulb thermometer. And it is natural to us to say that wet bulb temperature will be always lesser than that of dry bulb temperature in many cases, unless the water becomes completely saturated. Let's look into it a little bit more. So we have here a psychrometer, which is an equipment used to measure the dry bulb and the wet bulb temperature in the laboratory. The setup houses two thermometers as I have shown. They are set side by side. It's called as a sling psychrometer, and usually one will hold on the handle and they swing it across for about 1 minute before the readings are noted down. And the dry bulb thermometer, we see that the dry bulb is directly exposed to ambient condition, and the temperature that is indicated by that dry bulb thermometer is called as dry bulb temperature. Likewise, the bulb of wet bulb thermometer is covered with a soaked cotton wick, and the temperature is of that thermometer is called as wet bulb temperature, and the temperature of that thermometer is called as wet bulb temperature. Let us look into it a little bit more on dry bulb temperature and wet bulb temperature. So here we have a setup in which we have unsaturated air which is flowing through this apparatus. So since the air is unsaturated, that means it is relatively dry, and we see that first this sample of air is going to come across the vicinity of dry bulb of the thermometer, and the temperature that is indicated by this thermometer is called as a dry bulb temperature. And the same air is going to move further and approach the next thermometer, and the next thermometer is in the bulb of that is completely soaked with cotton wick, and it is dipped in a water, so it is completely saturated here. So what is happening here is, since the air is unsaturated and it is relatively at a high temperature, so we see that there is a heat transfer that is taking between the air molecules and the cotton wick. So cotton wick is relatively at a cold temperature, so we see that the heat from the dry air is going to penetrate into the cotton wick, and there is an evaporation which takes place across this. So since there is an evaporation, so there is a drop in the temperature in this thermometer. So this temperature, what is indicated, is called as wet bulb temperature, and the corresponding thermometer is called as wet bulb thermometer. And the same air is going to pass through this region through the duct. So we see that the temperature that is noted at the wet bulb temperature thermometer will be lesser as compared to the dry bulb thermometer. We know that this is obvious because of the cooling effect that takes place as a result of heat transfer between the air molecules and cotton wick. So we can write equation here, and the difference between the dry bulb temperature and the wet bulb temperature is called as wet bulb depression. Wet bulb depression is given as the temperature, that is a dry bulb temperature, minus the wet bulb temperature. So there is always a difference here as long as air is unsaturated. And this difference becomes very clear to us when we look at the sling psychrometer. When we see them together, then we see that on wet bulb thermometer the temperature will be only very little, whereas in the dry bulb temperature it will be shooted up much more higher as compared to the wet bulb thermometer. So we can clearly see the difference between the wet bulb thermometer and the dry bulb thermometer, and this difference is accounted as wet bulb depression. And these knowledge of this dry bulb temperature and the wet bulb temperature are very important when we have to look at the relative humidity. Let's move further, and a situation can arise when the dry bulb temperature can be equal to wet bulb temperature. So this is possible if suppose the air that is coming through this duct or through this passage, if it is fully saturated, that means there is enough amount of water vapor in the air, then that particular sample of air is called as a saturated sample of air. So that sample is in a no more position to absorb more amount of liquid. In that case, as it flows over the dry bulb thermometer, it indicates the temperature, whatever it indicates is the dry bulb thermometer, and as it flows over the wet bulb temperature, it is not going to absorb any more heat because the air sample is completely saturated. Therefore the wet bulb thermometer and the dry bulb thermometer both indicate the same temperature, so that is possible only when the air becomes completely saturated, the air sample is completely saturated. In that case, the wet bulb temperature will be equal to dry bulb temperature. Let's move further from here. So we have next is a super saturated air mixture. So far we have looked at what is saturated moisture and what is unsaturated moisture, and here we have super saturated moisture. So it is a mixture of water vapor and dry air in which the partial pressure of water vapor is greater than the saturation pressure of water at the temperature of the mixture. So in case of unsaturated moisture, we saw that partial pressure of the vapor is lesser than the saturation pressure of the water. In case of saturated moisture, we saw that the partial pressure of the vapor was equal to the saturation pressure of the water at the temperature of the mixture. So here we have a super saturated moisture in which the partial pressure of the vapor is greater than that of corresponding saturation pressure of the water. Now let us look at the next property, that is a dew point. So dew point, it is the temperature at which condensation of the vapor begins when the mixture is cooled at constant pressure. So let's understand this little more better considering TS plot. So here we have a TS plot and we have a saturation dome here, and then let's say that our moisture sample is on the superheated region. So we have a sample here, moisture sample, and it is, let's say that it is having some temperature, and that temperature is 45 degrees Celsius, and that particular temperature is nothing but measured by the dry bulb thermometer. Therefore this is a dry bulb temperature, and this is existing at some partial pressure, that vapor inside the moisture, and let's say that it is at some PV, partial pressure of the vapor. And now this sample of moisture, one can cool this, that means one can bring down its temperature. So when we cool this along the constant pressure, that means along this is a pressure curve, constant pressure curve, when we cool this along the constant pressure curve, then we see that the vapor which is there, that is water vapor inside the dry air, and as it approaches closer to the saturated vapor curve, it will be still under superheated region, but as soon as it touches the saturated vapor curve, there is a dew formation. That means the vapor begins to condense. Therefore, that particular temperature along the y-axis is called as a dew point temperature. Let's say this is at 30 degrees. So this is a temperature, and this temperature can also be a saturation temperature for the corresponding pressure. So now we see that we have a sample here, moist air, and the vapor inside this moist air is in superheated zone, and once we cool this along constant pressure condition, then the vapor begins to condense at a temperature when the sample approaches the saturated vapor curve. So that point where it begins to condense or a dew formation takes place, that is called as a dew point temperature. And the difference between the dry bulb temperature and the dew point temperature, this is called as a dew point depression. So which is the difference between the dry bulb temperature and the we have a dew point temperature. So here we have a dry bulb temperature and we have a dew point temperature. So in the earlier case we saw there is a wet bulb depression. So here this is another parameter called as a dew point depression. Both are different. Let's move further. Now let's look at next property, that is called as absolute humidity. This is also called as specific humidity, or it is also called as humidity ratio. Symbolically it is represented as W, or you may call it as omega. So this is a ratio of mass of vapor to the mass of dry air. So we have equation here representing the absolute humidity, which is given by small w, or say it is omega. Omega is equal to mass of vapor divided by the mass of dry air. So we know that atmospheric is a combination of dry air and the water vapor most of the time, and the amount of vapor to that of dry air, this ratio is called as absolute humidity. It is given by a unit kg of vapor to the kg of dry air, or simply kg by kg of dry air popularly. And using PV is equal to MRT equations, one can replace mass of vapor and one can express this equation as omega is equal to 0.622 partial pressure of vapor to the partial pressure of dry air. So this is a small derivation, and this numerical value what we are getting here, that is 0.622, comes because of the molecular weight of water to that of dry air. And one can further replace this pressure of air as total pressure minus pressure of vapor from our basic equation, that is total pressure is equal to partial pressure of air plus partial pressure of vapor. So once we rearrange this equation to get partial pressure of air, then the same equation gets a modified form. It takes the modified form as partial pressure of air is equal to total pressure minus the partial pressure of vapor. So we can replace now partial pressure of air, which is here, with the right hand side of the equation as P minus P vapor. So from now onwards we are going to consider this equation for omega as 0.622 partial pressure of vapor to that of partial pressure of total pressure minus partial pressure. So this is about the humidity ratio. Now moving to relative humidity, basically this indicates the degree to which an air vapor mixture or moist air is saturated, to what extent the moist air is saturated. So to have an idea about that, we have one property here called as relative humidity, which is expressed in terms of percentage. In short, one can call this as RH or pi. So we have equation here for relative humidity. RH or pi is equal to mass of vapor to that of mass of vapor at saturated conditions. So we have the same equation in terms of partial pressures as partial pressure of vapor to the saturated partial pressure of the vapor of the mixture existing at temperature T. So this is indicated usually in terms of percentage. So we can this knowledge about relative humidity is important as it talks about the extent to which a given sample is saturated. Let's move further and see what is the degree of saturation or saturation ratio, which is given by mu. So this is again a ratio of specific humidity. It's a ratio of specific humidity divided by to the specific humidity of saturated air at same temperature. So it is a ratio of specific humidity to divided by humidity, specific humidity of saturated air at same temperature. So this is by definition. So let's now understand about the saturation ratio with the TS plot. Here we have a TS plot and we have a saturation dome. Let's say that our sample, that is the moisture, is in the superheated region, and we know that it is having some partial pressure PV, and so we see that this moisture becomes saturated when it approaches the saturated vapor curve. So at the saturated vapor curve, again we have one more pressure curve, and the sample, when at constant temperature, when it is taken to the state point 2, and at this point the corresponding pressure will be the saturation pressure. So here we see that the sample of moist air becomes saturated when it approaches to the saturated vapor curve at a constant temperature condition. So here we are increasing the pressure, and thereby we take the sample from superheated region to that of saturated condition. So at this point we can say the sample is completely saturated. This ratio implies this process. So we have now the equation which we have earlier seen for the specific humidity as 0.622 and the partial pressure of vapor to that of total pressure minus the partial pressure of vapor. Now as the sample state point 1, as it approaches to and takes a new position, that state point 2, then the partial pressure of vapor becomes equal to that of partial pressure at saturation condition. Therefore one can replace PV with PSAT. So we have a modified equation here. So the same equation for the saturated condition. So since we are talking about degree of saturation, omega S or omega saturation condition, when the saturation pressure becomes equal to that of saturated vapor. So when both becomes equal, one can replace saturation vapor with saturated pressure. So this is about the degree of saturation. So friends, we have now looked at many properties related to moist air. So in the next class we will look at psychrometric chart and see about the role that is played by these properties. So with this we have come to the end of today's lecture. Thank you for your attention.